Hello everyone, and thank you for being here. We are group 32, and today we'll be presenting 2HADRAD, a portable life detection radar system. Our system is a battery-powered multimodal search and rescue device that's designed to detect human presence and provide actionable location data in emergency environments.
Shannon Hankinson, Electrical Engineering.
My name is Bailey Hitt, and I'm an electrical engineering student.
My name is Ryan Anderson, and I'm an electrical engineering major.
Hi, I'm Joshua. I'm studying computer engineering.
In situations like collapsed structures or low light conditions, it can be extremely difficult to quickly and accurately locate survivors. Our system addresses that by combining multiple sensing technologies into one platform. We fuse 24 GHz and 60 GHz radar, infrared thermal imaging with temperature compensation, and a UWB plus inertial navigation system to provide accurate detection and localization. By combining these sensors, this system can detect human breathing, body heat, and movement, and generate high-confidence detection along with 3D location estimation. When a target is identified, the system provides a real-time visual and audio alert, and it logs the data to a companion mobile app for further analysis and decision-making.
These are the core goals of our project. We are combining multiple sensing methods into one handheld system for environments where normal navigation or visibility is limited. UWB ranging helps estimate distance indoors where GPS is unavailable. The INS and barometer provide relative position and orientation tracking. An infrared sensor helps confirm human presence through body heat signatures. We display results directly on an LCD for immediate feedback, and the entire system is battery-powered for portability. Finally, the radar adds motion and respiration detection as well as heart rate, giving us another reliable method of identifying human presence. These goals represent the next level of system performance. We want the device to operate reliably in smoke-filled or low-light environments and improve positioning accuracy by incorporating GNSS when available outdoors. We also aim to optimize power delivery for longer runtime and improve the LCD interface for readability. Data transmission to an Android app through BLE expands usability as well as an iOS app. Our stretch goals include adding machine learning for better classification accuracy, radar detection through building materials, enhanced thermal mapping, positional mapping in the mobile app, and real-time battery monitoring on the display. These objectives turn our goals into measurable performance targets. The IR sensor should confirm human presence within 1 meter. The INS and barometer should estimate relative location within 2 meters. Detection feedback should appear on the LCD within 5 seconds, while a red LED indicator activates in under 1 second. Buttons allow the user to mark victim locations, reset the system, control power, and navigate menus. The battery subsystem should power the device for at least 2 hours continuously. Finally, radar should detect human distance and respiration within 2 meters. These are measurable targets for higher performance. We want radar to maintain at least 90% detection accuracy in cluttered or noisy environments. The radar should also detect a human subject in line of sight conditions at 2 meters or more. Outdoors, when GNSS is fused with INS data, we aim for localization accuracy within 4 meters. LCD readability should exceed 90% legibility in bright field conditions. BLE data should transmit to the Android app within 5 seconds, and the power system should improve runtime by at least 25% while keeping power draw under 10 watts. These stretch objectives push the project beyond baseline requirements. We want to demonstrate human detection through 1 inch of drywall with at least 80% accuracy. Another target is a hazard awareness layer that can identify 3 possible risks using fused sensor data. We also plan to add adjustable UI controls, multiple detection modes, and heat map visualization with quick response times. Real-time battery monitoring would display charge percentage and estimated runtime. Finally, the Android application could support live positional mapping with less than 2 seconds of latency. This slide summarizes the measurable engineering specifications for our system. On the left are the primary performance targets, including radar detection range of up to 2 meters in line of sight conditions, overall detection accuracy of at least 90%, and average system power consumption under 10 watts. The rechargeable battery should support at least 2 hours of operation. User feedback through the LCD and speaker should occur within 5 seconds. The IR sensor is targeted to confirm human presence within 1 meter, and localization accuracy is targeted within 4 meters using fused sensor data. On the right, these requirements are broken down by subsystems so each component has clear design responsibilities. This house of quality translates customer needs into engineering requirements. On the left are customer priorities such as detecting victims, reliability, battery life, portability, and cost. Across the top are measurable technical metrics like detection range, response time, battery life, power consumption, weight, and cost. The symbols in the matrix show positive or negative relationships between customer needs and engineering decisions. This helps us prioritize design trade-offs so we focus on what provides the most value while meeting practical constraints like budget and power.
On this slide, we have our hardware block diagram outlining the overall hardware structure. At the top, we have our sensor subsystem, which includes the inertial navigation system stack, our infrared thermal sensor, ultra-wideband module, and the ultrasonic sensor. Below that is the radar module, which is 60 gigahertz. Then in purple, we have the MCU, which is fed into each of these blocks with the sensors, the user interface, the radar module, and the sensor subsystem. Next to that in green, we have the power subsystem, including a 5 volt and 3.3 volt buck regulator with the lithium ion battery into the battery management chip. And finally, at the bottom, we have the user interface, which includes the 5-way navigational button, our touchscreen module display, and the speaker, audio amplifier, and the red LED. Breaking down each block, first we have the sensor subsystem and MCU. The sensor subsystem, as we previously discussed, includes the inertial navigation system, the infrared thermal sensor, ultra-wideband module, and ultrasonic sensor. Each is outlined on the PCB off to the right, where the ultra-wideband communicates through SPI. The inertial navigation system is a combination of UART and I2C, where UART is the GPS GNSS, which is partially covered by the PCB there. And the other components are I2C. The infrared thermal sensor is I2C, the ultrasonic sensor is GPIO, and then in the center of the board we have the microcontroller unit, the ESP32.
The user interface subsystem can be seen below in pink. Everything on this PCB is powered by the 3.3 volt rail. First up, we have the red LED, which we have programmed to turn on every time the radar is active to alert the user to stay away from the radar at least 20 to 30 centimeters. Then we designed an audio amplifier. This will alert the user whenever the power system is running and also when a human is detected, and we will probably add some more audio alerts in there. Then we have the LCD, which is the main component of the user interface system. It shows the heat map, the map of the location of the victim, and it also displays a screensaver whenever the system is idle. And then we also designed a 5-way navigational button on this PCB to allow the user to navigate the screen without touching it for environments where it might be wet or the gloves are too heavy. And everything on this board connects to Shannon's board with the ESP32 through screw terminals.
This slide highlights our 60 GHz radar subsystem using the TI IWR6843 AOP module. On the left is the internal block diagram showing the RF front end, ADC, DSP core, ARM control core, and external interface. This radar transmits and receives signals to measure motion, distance, and micro movements such as breathing. On the right is our hardware integration using UART communication with the main controller. This radar is one of the most important sensors because it can detect human presence even in darkness or visually obscured environments. This slide shows the power subsystem that makes the device portable. We use a 3-cell lithium-ion battery pack providing approximately 9 to 12.6 volts depending on charge level. A battery management board handles protection and charging functions. That voltage is stepped down through dedicated buck converters, the LM2576s, to create stable 5 volt and 3.3 volt rails for our electronics. The 5 volt rail powers higher load devices such as the radar, while the 3.3 volt rail supports logic and sensors such as the MCU. This design gives safe, efficient, rechargeable operation for field use.
For a division of responsibility, the power subsystem is owned by Ryan, as Bailey is a secondary support. For the sensor subsystem, myself, Shannon, was the primary, as Bailey supporting me as secondary. The radar module, Ryan, is the primary, as myself as a secondary. The MCU, Joshua was the primary, as myself, Shannon, as the secondary. And the user interface, Bailey Hitt, was the primary, as the secondary was Joshua.
This enclosure is a 9.5 by 8 by 5 inch 3D printed case manufactured using PETG. We chose PETG because it offers a good balance of strength, heat resistance, and durability, which is important for a handheld device that may operate in outdoor or high temperature conditions. It's also less brittle than PLA, so it holds up better under mechanical stress. This case is designed with a stacked modular architecture to separate sensitive components and improve overall system performance. The system in the front, we have the user interface plate, which is the pink layer. This includes cutouts for the LCD screen, speaker, button, and LED indicators, and the power switch. The LEDs are routed through a flexible light pipe, which improves visibility while maintaining a clean and protected design. The case also features ergonomically designed handles, which allows the user to comfortably hold the device while maintaining a safe distance from the radar. Behind that, the next layer is the power board, shown in green, followed by the sub-sensor system in blue. These layers are physically separated to help reduce electrical noise and interference between subsystems. The radar is isolated on its own plate in an L-shaped configuration, which helps block interference from other components. This section is lined with a grounded aluminum foil tape, which acts as a simple EM shield to improve signal integrity. On the back of the enclosure, we have cutouts for the USS, infrared thermal camera, and radar, along with ventilation slits that are primarily aesthetic but also allow for minor airflow. In addition to the main unit, we developed a secondary handheld module for the UWB system. This smaller enclosure includes its own LCD, power switch, and radar module, which works in conjunction with the primary system. This unit follows a similar stack design. The top layer contains the user interface, the second layer houses the battery, the third layer contains the UWB module and microcontroller, and the bottom layer isolates the radar, again using the L-shaped shield structure with the grounded aluminum tape. Overall, this modular and layered design allows us to minimize interference, improve reliability, and maintain a compact, user-friendly system. It was also intentionally designed for serviceability, allowing individual boards and subsystems to be individually accessed, debugged, or replaced, which reduces downtime and simplifies future iterations.
Next, let's discuss software design. These diagrams summarize the program's functionality, but in simple terms, our device will be collecting data from the radar, the infrared, and the navigation sensors to provide the user with a radar map displaying the surrounding radar detections of human vitals, a heat map displaying heat signatures from the surroundings, and location tracking on a map. The device will function in operating modes in which certain sensors will be continuously sending data to the MCU. From there, it processes the data and returns confidence scores based on how confident it is that a human has been detected, based on heat, breathing, or heartbeat signatures. In addition, the user can also place their own markers on the map to keep track of where they've traversed and any victims around them. At any point, the user can connect our device to a mobile app where they can see the device data and also save records of their activity and past human detection information. And this is all connected through Bluetooth. Here is our use case diagram, which reiterates our functionality. The location traversal, marking positions, radar map and thermal map that automatically detect human signatures, and a mobile app providing additional utility and convenience for first responders. Our flowchart goes into detail about our user interface. The user is presented with 4 operating modes: thermal, radar, INS, and scan mode. Thermal mode displays the heat map and heat signature detections. Radar mode displays the radar map and radar detections. INS mode displays the location traversal and allows victim location marking. Scan mode is a combination of the other 3 modes. It starts a session that undergoes phases of detections, with radar first, then thermal, then location, and then it offers a summary of the session. Here are some pictures of our device user interface. You can see the screensaver, the main menu, which offers the 4 modes that our device operates in, as well as the button to connect to the mobile apps. And you can see how our thermal map, radar map, location INS map, and our scan mode look. And here are some screenshots from the Android version of the mobile app we have for this device. You can see our main menu allows us to press connect, in which case, if both the app and the device are trying to connect, they will establish a connection. And on the app, you can navigate to the same four operating modes that the device operates in, and you can see the data relevant to each mode. So you can see the data for the thermal mode, radar mode, and the INS mode, which also, because we have this feature available on apps, allows us to connect to a live map um, when we get location data from the device.
Part of the software design includes a smartphone iOS application. This application mimics the menu and the screens on each tile from our handheld unit. At the top left, you can see the thermal, radar, INS, and scan tiles, which mimic the exact menu on our handheld unit. When you go into the thermal screen, you can see the thermal map array with the relevant data below it, just like on our handheld unit screen. And then the INS map and the radar maps are also replicas of the handheld unit's information, so users are able to see in real time what data is being collected.
So finally, this is our budget. It's broken down between the radar module and PCB, other PCBs, and the various sensors and peripherals that we've required. The radar module has ended up being pretty costly compared to the other parts, and towards the completion of our project, we've had to reorder or replace some parts, but the budget's mostly stayed within our expectations for the project.